All right, I'm here on the bottom of page 229. You can see there's just a summary of the types of equations that you might find yourself writing for lines in 3 dimensions. So vector forms, parametric form, and symmetric form. I find parametric form to be by far the most useful, and I will use it more often than the others by far. Then vector form comes next. Pretty much always use that top form there. So this is the one when I do use vector form that I find myself using. But I'm like a 95% parametric type guy. So that's what I'll be doing for most of these problems, unless they stipulate otherwise. So now what I want to do is, I guess, some practice problems. So let's take a look at these. So find the vector, parametric, and symmetric equations of the line passing through 1, 6, -5 with direction vector. So we're given the direction vector. The direction vector, just another way of saying vector parallel to the line, so we don't have to find one in this case. So vector, parametric, symmetric. All right, let's do it. So I'm gonna switch to a black pen, I guess. And for vector, it's gonna be, we make a generic vector using our point, right? So x, y, z is a generic point, 1, 6, -5 a definite point, and now I'm just gonna make a vector out of this. So it's gonna be x minus 1, y minus 6, z plus 5 equals. So this generic vector has to be parallel to the direction vector. So it's going to be t, and then -3, 4, and 7. And that's it. That's the vector equation of the line. Okay, so, and I should probably say that so that whoever's reading this, like all of you, know that this is a vector equation. So you don't want to just like throw all of them out there and hope that the reader knows what you're talking about. So let's do parametric, right? So parametric, we could convert the vector into parametric, but I'm just gonna like write them without that. I'm gonna write it as if I hadn't previously done the prior problem, whatever. 1, 6, -5, minus 3t plus 4t plus 7t. There you go. Couldn't be simpler than that one. And then we want the symmetric equation. So for the symmetric equations, I usually go from the parametric and just kind of like do it in my head. So it's going to be, so you take the x thing, you're going to subtract 1, divide by -3. You usually don't simplify that, right? Like some of you probably are like, ooh, I should take the negative sign from the denominator, move it up to the numerator, do like 1 minus x over +3. You don't want to do that because when we're done, you want to be able to see the vector. So I'm going to keep going. Y minus 6 over 4. And then that 6 really looks like a b. Like if I saw that, I would think that's probably a b. Z plus 5 over 7. So what I mean by see the vector is look at those denominators and compare them to our vector, and you can see the vector. So if you start messing around with those negative signs, you're not going to be able to see the vector, and you kind of like lose sort of the geometry of the situation, and you got to like think about it a lot more. So don't oversimplify. All right, find the vector equation of a line orthogonal to the line in the previous example, but still passing through the point 1, 6, -5. So orthogonal to the previous line. So orthogonal, if you recall, which I'm sure you do. Whoa, I just opened, I don't know if you could hear that. I just opened Siri. What did I say that sounded like that? Nothing. All right, here we go. So orthogonal vectors, or orthogonal lines, perpendicular lines, right? They're gonna be like this, which means that their direction vectors, let's use some different colors here. They're gonna be like this guy, and then maybe like this guy, right? So they're orthogonal to each other, which means I need to find a vector whose dot product with this vector is 0. So what I'm going to do is kind of this neat little sort of trick thing. I'm going to make up 2 of the components of the vector, and then I will solve for the third component. So I know that the dot product needs to be 0. So I'm going to make up my vector. This will be the direction vector for my line. V, I guess, is, I'm going to say it's, I don't know, 1, 2, and then C. And then I know that if I do, got to be able to see that vector. If I do V dot -3, 4, 7, I'm going to have to get 0. So let's actually do the dot product. So it's 1 times -3 is -3. 2 plus 4 is 2 plus 4? 2 times 4 is 8. Did you hear that? I was going to do it wrong too. I was like 2 plus 4 is 8. And then 7C equals 0. So I get 5, 5, -5, -5 over 7. So that C is -5 over 7. So my vector would be 1, 2, -5 over 7. Nobody wants to use that vector though, right? Because of the over 7 part. So what I'm going to do to make my life a little easier, I'm going to use, let's see, the notation for this, I played a little loose with this. So I'm just going to say use, I'm going to multiply 3 by 7. 7, 14, -5. And then we could check, I guess, you get, I don't want to do that. I get 21, -21, and then -35 is -46, 56, -56, and then 4 times 14 is +56, so that works. All right, so this is my vector, my direction vector, and so my line is going to be x equals y equals z equals. It's going to be 1, 6, -5, and then plus 7t plus 14t and minus 5t. This is the equation of a line that is orthogonal to the line in the previous example. But then we have this next question, which if you weren't already thinking about it, you will now. How many answers are there to this particular question? So in 2 dimensions, there's one answer to this question. But what can happen in multiple dimensions, in 3 dimensions, is we start out with say this is our line. We found a line that's perpendicular. But think about rotating this line. All of the lines that I'm rotating are also orthogonal. There's an infinite number of answers. So let's write that. There's an infinite number of solutions. Now think about this, or do it, right? Like put your pencil or pen on your desk and rotate it, right? So one answer to what do they all have in common is that they're all orthogonal to that given line. Obviously, that's going to be true. They all go through the same point, also true, because they had to go through that point. More interesting though, think about the surface. If you put it down on a desk or a table, think about the surface that you put it on and then rotated. So when we rotated it, I did that as if you could see. They're all in the same plane. Every one of the solutions to this falls in the same plane. So there's an infinite number of solutions. They're all in the same plane. So maybe what we could do is we could jump into GeoGebra and see if we can just illustrate that, and then I will come back to these. So let me share a GeoGebra thing with you. Okay, so what I want to do is I'm going to graph, gotta rearrange this, get it bigger on my screen, probably bigger on your screen. I don't have any idea. I'm going to do 3D graphing, 3D. Okay, so I'm going to plot the original line, which was, so curve, 1 plus 7t, 6 plus 14t, and -5 minus 5t. T, choose your own adventure. I'm gonna go like -3 to 3, just so I can like see it. But I kind of can't see it, so I'm gonna zoom out a bunch. Oh, way too much. Way too much. Come back. So this is like our line. You know, -3 to 3 is just not doing it for me. Let's go like -10 to 10. See a lot of it. Oh, it's the box thing again. It gets me every time, right? The line passed out of the box that we can see. So the box kind of like extends up from the sides of that plane and down a little bit, and it goes to the bottom of the z-axis, and top of the z-axis. Gets me every time. I do not know why I fall for that so often. I'm gonna do a thing. I'm gonna click and do this. There you go. Now we can see it. Ooh, and now I'm moving that. Rotate. There we go. Okay, so that's the line. Let's put the point 1, 6, -5. 1, 6, -5. All right, let me zoom out. And that's a pretty okay picture of it, I guess. Let's put the line that we found so far. So I'm gonna do curve. What are you? 1 plus 7t, comma 6 plus 14t, comma -5 minus 5t, comma t, comma -10 to 10. And I don't see anything. Why don't I see anything? 7, 14, -5, minus 5, 1, 6, -5. These are like the same. Wait, everybody. I graphed the same line twice. Hold on. You were probably yelling about that, right? Like I can hear you from here. Like, oh, that first line, it's the wrong line. There's just nothing you can do about it. If we were in class, you could yell at me and I would be like, what are you talking about? But now I get it. Okay. Am I looking at the right thing? I hope so. Let's find out. Okay, they look orthogonal for sure. All right, so what I need now is I need more vectors that are orthogonal. I'm going to switch over to the Inspire and see if I can get a bunch of those. So new share, Inspire, and all right. So I'm gonna solve, and I'm gonna feed it this vector. What's the given vector? -3, 4, 7. Oh wait, dot. I want to dot these. Dot product. Menu 3C 2 or 3 maybe, and then it's -3, 4, 7. I mean, I could just do it. All right, I'm gonna make up two things. So I'm gonna do I don't know, -2, 5, C. I want the dot product to equal 0. Solve for C. Okay, so then it's -2, 5, -26 over 7. That 7 is suspicious, right? It's the same number that showed up last time. And then I'm going to multiply by 7. So I need to use -14, 35, and -26. -14, 35, 26. What are the chances I can remember that as I switch back over here? I will tell you right now, it's 0 because I'm talking through it and no one could remember that. All right, so let's see. Kind of rearrange my screens a little bit and maybe I can see it. Get out of the way. All right, I'm on it. Don't worry, everybody. Here we go. Duplicate. And all I have to really do is change this. So -14, 35, and -26. All right, you're being extremely patient. I appreciate that. So we can see. Can we see? I mean, are they orthogonal to it? I feel like. Oh, you know what happened? It's because of the way that okay, hold on. Zoom way out. I changed the scale there. And then this is a disaster. Here we go. Let's move over. Let's move up. Can we move up more? Let's move over more. Oh, there. Bring it toward us, I guess. And rotate. This is definitely the best video I've ever made. I think we can all agree on that. All right, if you'll bear with me, I'm gonna do one more. I'm just gonna do it over here. So you just stare at that for a second. I'm gonna create another vector for us. So 9 and maybe like -8. This feels like it'll be unique. Okay, and then I got 9, -8. Calculator tells me 59 over 7. 7 again. What is going on? So I'm going to multiply by 7. Okay, 63, -56, +59. Let's duplicate. So we got to go with 63. So these are all, I'm just like I'm picking 2 random things, just whatever. And then I'm solving for the third one, which guarantees that the dot product is 0. And if anyone's still with me, I'm really happy about that because this is going forever. Okay, I get this. And there it is. Sometimes it's hard to orient it so that you like can tell that they're orthogonal. So look at those 3 lines. They're all forming a plane. And so the next thing we want to do is find the equation of that plane. So I'm going to come back in the next video and I'm going to find the equation of that plane. All right, so hope you're finding this helpful.